Hello everyone, on today's class we're going to go through the Ergun equation for a packed bed reactor. This here is the Ergun equation. It's used to study the pressure drop or the change in pressure inside a packed bed reactor with respect to the axial distance. We'll be working with a gas phase in this derivation, and the reason behind that is because in a liquid phase, the liquid doesn't change pressure throughout the reactor, causing no change in density, and therefore this equation is not necessary, the Ergun equation. Therefore, the Ergun equation only applies when we're working with a gas phase in a packed bed reactor. So some of the factors that are used in the Ergun equation are density, which is right here, gravity, this term here, the particle diameter, which is the diameter of the packings or the catalysts inside the reactor, the void fraction, which is basically the distance between the packings. Okay, that's the void fraction. And G, which is the superficial mass velocity, which is basically a differential amount of mass that is traveling from one point to the other, and that's the velocity of that mass. The superficial mass velocity is a velocity of a differential amount of mass moving from one point to the other. Okay, so these are the factors that affect the Ergun equation. Now for this class, we'll first cover the material balance of a packing bed reactor. I believe we've done that in a previous class, but the derivation was done in terms of a liquid phase, where we used this equation here for the concentration. This equation is only used for a liquid phase, whereas in the gas phase, the concentration is a function of pressure, temperature, and density, which in a previous class I derived that the final concentration equals Ca naught 1 minus x divided by 1 plus epsilon x times P over P naught times T naught over T. If you do it a couple of times, it'll become second nature. So yeah, our material balance of the packed bed reactor in this class will be in terms of the final concentration in a gas phase. Okay, gas phase. So let's go ahead and start that. We'll always start with input minus output plus generation equals accumulation. The input is the moles flowing in minus the moles flowing out. Generation is rate of reaction prime, RA prime, which signifies that the rate of reaction is in terms of mass, not volume. Okay, the mass is the mass of the packings or the catalyst times dW, change in mass of the packing or the catalyst. The accumulation equals 0 because it's steady state. We're assuming it to be in steady state. Okay, we'll go ahead and solve for dW, and that will equal dFA. Okay, we move these two terms to the other side, which gave us FA minus FA naught, which can also be written change in FA or dFA. Okay, Therefore, we got this. Now, we will move dw to the other side. Am I missing something? Okay, so I'll move dw to the other side. So RA prime equals dFA over dW. Now, we know that FA equals FA naught 1 minus x, okay? Which can also be written as FA naught minus FA naught x. Now, the derivative of dFA in terms of dx equals negative FA naught. Therefore, dFA equals negative FA naught dx. And we're going to substitute that here in this term because we want to change dFA in terms of conversion. Okay? So RA prime equals negative FA naught dx over dW. I'm going to move this term to the other side. For the rate of reaction, prime, we will assume it to be in a first order, just for simplicity. So, dx over dw equals negative k CA over negative FA naught. Okay, these two signs can cancel out. Now, dx over dw equals KCA over FA naught. Now, this CA here, since it's in terms of a gas phase, we need to substitute the equation of the final concentration when it's in a gas phase, okay, which is, I wrote it on top, but I'll write it again, it's not a big deal. Therefore, dx over dy equals k CA naught 1 minus x over FA naught times 1 plus epsilon x times P over P naught times T naught over T. Okay? And that is your material balance in terms of a final concentration that takes into consideration the gas phase, which takes into consideration the change in pressure, change in temperature, and change in density. Okay, so the dx over dw is a function of x and p. Okay, you might say, hey, why is it not a function of temperature? For simplicity, we're assuming it to be an isothermal, so we don't have to take into consideration three changing variables. But the question is, we want to change this factor, pressure, and relate it to W, because we want this equation here to relate both conversion and the weight of catalyst, which P is not so far, so we need to find an equation that relates dP with dW, and we'll do that on the next class. Stay tuned.